Section 8.4, Resilient Applications with Reactive Spring. Resilience is about keeping a system available and delivering its services, even when failures happen. Since failures will happen, and there's no way to prevent them all, it is critical to design fault-tolerant applications. The goal is to keep the system available without the user noticing any failures. In the worst-case scenario, the system may have degraded functionality, graceful degradation, but it should still be available. The critical point in achieving resilience, or fault tolerance, is keeping the faulty component isolated until the fault is fixed. By doing that, you'll prevent what Michael T. Nygaard calls crack propagation. Think about Polar Bookshop. If catalog service enters a faulty state and becomes unresponsive, you don't want order service to be affected as well. Integration points between application services should be carefully guarded and made resilient to failures affecting the other party. There are several patterns for building resilient applications. In the Java ecosystem, a popular library for implementing such patterns was Hystrix, developed by Netflix, but as of 2018 it entered maintenance mode and will not be developed further. Resilience 4J gained a lot of popularity, filling the void left by Hystrix. Project Reactor, the Reactive Spring Stack Foundation, also provides some useful features for resilience. In this section, you'll make the integration point between order service and catalog service more robust, using Reactive Spring to configure timeouts, retries, and fallbacks. In the next chapter, you'll learn more about building resilient applications with Resilience 4J and Spring Cloud Circuit Breaker. Section 8.4.1, Timeouts. Whenever your application calls a remote service, you don't know if and when a response will be received. Timeouts, also called time limiters, are a simple yet effective tool for preserving the responsiveness of your application in case a response is not received within a reasonable time period. There are two main reasons for setting up timeouts. If you don't limit the time your client waits, you risk your computational resources being blocked for too long, for imperative applications. In the worst-case scenario, your application will be completely unresponsive because all the available threads are blocked, waiting for responses from a remote service, and there are no threads available to handle new requests. If you can't meet your service level agreements, SLAs, there's no reason to keep waiting for an answer. It's better to fail the request. Here are some examples of timeouts. Connection timeout. This is the time limit for establishing a communication channel with a remote resource. Earlier, you configured the server.netty.connection timeout property to limit the time Netty waits for a TCP connection to be established. Connection pool timeout. This is the time limit for a client to get a connection from a pool. In Chapter 5, you configured a timeout for the Hikari connection pool through the spring.datasource.hikari.connection timeout property. Read timeout. This is the time limit for reading from a remote resource after establishing the initial connection. In the following sections, you'll define a read timeout for the call to the catalog service performed by the book client class. In this section, you'll define a timeout for book client so that if it expires, the order service application will throw an exception. You can also specify a failover instead of throwing the exception to the user. Figure 8.7 details how the request-response interaction will work when timeouts and failovers are defined.
Figure 8.7. When a response is received from the remote service within the time limit, the request is successful. If the timeout expires and no response is received, then a fallback behavior is executed, if any. Otherwise, an exception is thrown.
Defining a timeout for web client. Project Reactor provides a timeout operator you can use to define a time limit for completing an operation. You can chain it with the result of the web client call to continue the reactive stream. Update the getBookByISBN method in the book client class as follows to define a timeout of 3 seconds.
Listing 8.23. Defining a timeout for the HTTP interaction.
Instead of throwing an exception when the timeout expires, you have the chance to provide a fallback behavior. Considering that order service can't accept an order if the book's availability is not verified, you might consider returning an empty result so that the order will be rejected. You can define a reactive empty result using mono.empty. Update the getBookByISBN method in the book client class as follows.
Listing 8.24. defining timeout and fallback for the HTTP interaction.
Note: in a real production scenario, you might want to externalize the timeout configuration by adding a new field to the client properties. In that way, you can change its value depending on the environment without having to rebuild the application. It's also essential to monitor any timeout and tune its value if necessary. Understanding how to use timeouts effectively. Timeouts improve application resilience and follow the principle of failing fast. But setting a good value for the timeout can be tricky. You should consider your system architecture as a whole. In the previous example, you defined a 3-second timeout. This means that a response should get from catalog service to order service within that time limit. Otherwise, either a failure or a fallback occurs. Catalog service, in turn, sends a request to the PostgreSQL database to fetch the data about the specific book and waits for a response. A connection timeout guards that interaction. You should carefully design a time-limiting strategy for all the integration points in your system to meet your software's SLAs and guarantee a good user experience. If catalog service were available, but a response couldn't get to order service within the time limit, the request would likely still be processed by catalog service. That is a critical point to consider when configuring timeouts. It doesn't matter much for read or query operations because they are idempotent. For write or command operations, you want to ensure proper handling when a timeout expires, including providing the user with the correct status about the operation's outcome. When catalog service is overloaded, it can take several seconds to get a JDBC connection from the pool, fetch data from the database, and send a response back to order service. In that case, you could think of retrying the request rather than falling back on a default behavior or throwing an exception. Section 8.4.2 Retries. When a service downstream doesn't respond within a specific time limit, or replies with a server error related to its momentary inability to process the request, you can configure your client to try again. When a service doesn't respond correctly, it's likely because it's going through some issues, and it's unlikely that it will manage to recover immediately. Starting a sequence of retry attempts, one after the other, risks making the system even more unstable. You don't want to launch a DOS attack on your own applications. A better approach is using an exponential back-off strategy to perform each retry attempt with a growing delay. By waiting for more and more time between one attempt and the next, you're more likely to give the backing service time to recover and become responsive again. The strategy for computing the delay can be configured. In this section, you'll configure retries for Book Client. Figure 8.8 details how the request-response interaction will work when retries are configured with exponential back-off. For example, the figure shows a scenario where each retry attempt's delay is computed as the number of attempts multiplied by 100 ms, the initial back-off value.
Figure 8.8. When catalog service doesn't respond successfully, order service will try at most 3 more times with a growing delay.
Defining retries for Web Client. Project Reactor provides a retry when operator to retry an operation when it fails. The position where you apply it to the reactive stream matters. Placing the retry when operator after timeout means that the timeout is applied to each retry attempt. Placing the retry when operator before timeout means that the timeout is applied to the overall operation. That is, the whole sequence of the initial request and retries has to happen within the given time limit. In Book Client, we want the timeout to apply to each retry attempt, so we'll use the first option. The time limiter is applied first. If the timeout expires, the retry when operator kicks in and tries the request again. Update the getBookByISBN method in the Book Client class to configure a retry strategy. You can define the number of attempts and the minimum duration for the first backoff. The delay is computed for each retry as the current attempt number multiplied by the minimum backoff period. A jitter factor can be used to add randomness to the exponential of each backoff. By default, a jitter of at most 50% of the computed delay is used. When you have multiple instances of order service running, the jitter factor ensures that the replicas will not retry requests simultaneously.
Listing 8.25. Defining retries with exponential backoff for the HTTP call.
Understanding how to use retries effectively. Retries increase the chance of getting a response back from a remote service when it's momentarily overloaded or unresponsive. Use them wisely. In the context of timeouts, I highlighted the need for handling read and write operations differently. When it comes to retries, this is even more critical. Idempotent requests like read operations can be retried without harm. Even some write requests can be idempotent. For example, a request to change the author of a book with a given ISBN from S.L. Cooper to Sheldon Lee Cooper is idempotent. You could perform it a few times, but the outcome will not change. You shouldn't retry non-idempotent requests, or you'll risk generating inconsistent states. When you order a book, you don't want to be charged multiple times just because the first attempt failed due to the response being lost in the network and never received. When retries are configured in a flow where the user is involved, remember to balance resilience and user experience. You don't want users to wait too long while retrying the request behind the scenes. If you can't avoid that, make sure you inform the users and give them feedback about the status of the request. Retries are a helpful pattern whenever the service downstream is momentarily unavailable or slow due to overloading, but it's likely to heal soon. In this case, you should limit the number of retries and use exponential backoff to prevent adding extra load on an already overloaded service. On the other hand, you shouldn't retry the request if the service fails with a recurrent error, such as if it's entirely down or returns an acceptable error like 404. The following section will show you how to define fallbacks when specific errors happen. Section 8.4.3 Fallbacks and Error Handling. A system is resilient if it keeps providing its services in the face of faults without the user noticing. Sometimes that's not possible, so the least you can do is ensure a graceful degradation of the service level. Specifying a fallback behavior can help you limit the fault to a small area while preventing the rest of the system from misbehaving or entering a faulty state. In the previous discussion of timeouts, you already provided a fallback behavior if no response is received within the time limit. You'll want to include fallbacks in your general strategy to make your system resilient, and not just in a specific case like timeouts. A fallback function can be triggered when some errors or exceptions occur, but they're not all the same. Some errors are acceptable and semantically meaningful in the context of your business logic. When order service calls catalog service to fetch information about a specific book, a 404 response might be returned. That's an acceptable response that should be addressed to inform the user that the order cannot be submitted because the book is not available in the catalog. The retry strategy you defined in the previous section is not limited. It will retry the request as long as an error response is received, including acceptable ones like 404. However, in that case, you don't want to retry the request. Project Reactor provides an on-error resume operator to define a fallback when a specific error occurs. You can add it to the reactive stream after the timeout operator and before the retry when, so that if a 404 response is received, web client response exception not found exception, the retry operator is not triggered. Then you can use the same operator again at the end of the stream to catch any other exception and fall back to an empty mono. Update the getBookBysBN method in the book client class as follows.
Listing 8.26 Defining exception, handling and fallbacks for the HTTP call.
Note: in a real-world scenario, you would probably want to return some contextual information depending on the type of error, instead of always returning an empty object. For example, you could add a reason field to the order object to describe why it's been rejected. Was it because the book is unavailable in the catalog, or because of network problems? In the second case, you could inform the user that the order cannot be processed because it's momentarily unable to check the book's availability. A better option would be to save the order in a pending state, queue the order submission request, and try it again later, using one of the strategies I'll cover in Chapter 10. The key goal is designing a resilient system that, in the best-case scenario, can provide its services without the user noticing that there has been a failure. In contrast, in the worst-case scenario, it should still work but with graceful degradation. Note: Spring WebFlux and Project Reactor are exciting subjects in the Spring landscape. If you want to learn more about how Reactive Spring works, I recommend looking at Reactive Spring by Josh Long, reactivespring.io. In the Manning catalog, see Part 3 of Spring in Action, 6th edition, by Craig Walls, Manning, 2022. In the next section, you'll write automated tests to verify the different aspects of the order service application.